Let's say you're in your car, traveling at 5 meters per second. Your friend has a timer and she starts her stopwatch. First, it shows 0. 10 seconds later, here you are, still going at 5. Your friend asks, how far did you travel? And you say, I used this equation because my speed was constant. We're looking for how far, and that's the distance, so we rearrange so that distance is isolated. And then we plug in the values. The distance is the speed times the time we were traveling, and that gives 50 meters. Now, let's say you have a more complicated situation. Instead of a constant speed, your speed is changing. So when the stopwatch shows 0, you're moving at 2 meters per second. Then later, you're moving at 4, and then you slow down to 3, and then you speed up to 5, and you speed up to 7. Your speed is changing randomly, speeding up, slowing down. So how do you find the distance? You can't really use this equation because you have to have a constant speed for this equation to apply. Here's how we can solve this problem. We're going to break the trip into chunks or intervals of time. For this first interval of 1 second, I'm going to assume that the speed was constant, even though it wasn't. The constant speed, I'll assume, was the starting value of 2, and I calculate the distance traveled. In the first interval, we plug in that constant speed of 2, even though it wasn't actually constant, and it was traveling for 1 second. Now we move to the second interval. Again, the speed was changing here, but we're going to assume that the speed was constant, and we'll use the starting value of 4. We calculate the distance using that constant speed of 4, even though the speed was actually changing. Then we move to the third interval, and again, we assume that there's a constant speed over this interval or chunk, and we're going to use the starting value of 3. You calculate the distance. We move to the final interval, and we assume the constant speed was 5, the initial value, and again you calculate. Now, this is not a great way to do the calculation. For one, this final speed here was 7, and we haven't used the value 7 anywhere in this equation. But we go ahead, we calculate the distance for each chunk or segment, and we add all of those distances together to get the total. Now, graphically, here's what we're doing. We're breaking the trip into chunks. We're assuming that there is a constant velocity for each chunk. So here's the first segment down here, the first chunk, the first interval. Our constant speed was 2. So from 0 seconds to 1 seconds, there's the constant velocity. And then, here's the second interval down on the bottom. The speed jumped up to 4. So it jumps up on the graph to a y value of 4 meters per second. And it stayed there for the entire interval. And then it jumped to 3. So it fell down, and it stayed there for the entire third second. Let me bring up the last segment. It jumped up to 5, and it stayed there for the entire final second. When we calculate our distance this way, we got a value of 14 meters. Now let's try and figure out just how bad this is. Here are the data points, the speeds, and the graph actually looks like this. And as you can see, the speed isn't constant. It's changing all the time. The true distance using the true graph is 17.2 meters. So what can we do to try and improve our value? How can we get this 14 a little closer? Well, one thing is, instead of assuming that the speed is constant over an entire second, let's assume the speed is constant over a much smaller interval of time. Let's take an interval of 0.1 seconds. So instead of getting the velocity every 1 second, here it is every 0.1 seconds. And you can already see we're going to get a better value because this looks a lot closer to the true graph. Okay, so we assume that the speed is constant for this 0.1 seconds, and then it jumps up, and we assume it stays constant for the next 0.1 seconds, and then it jumps up, and then we assume it stays constant. We continue in this fashion. We calculate every little distance with every constant speed, and what do we get down here? Our estimate is 16.9, and that's a lot closer to the true value of 17.2. So we can actually make this assumption. We can assume the speed is constant and then just calculate all the many different values. The only trick is you need a small interval of time. So here's that data in Excel. You've got the graph, and this is the first case where I'm using an interval of 1 second. So here's the speed after each 1 second, and I calculate the distance for each interval. In the first interval, even though the speed changes, I assume it's always the 2.0. I multiply the speed by the delta t, the increment is 1, and that gives me the distance in the first interval. Then I calculate how far we travel in the second interval, and I assume we move at a constant speed of 4. I multiply the 4 times the time, which is from 1 to 2 seconds, so the delta, the increment, is 1 second. Again, here we assume that from 2 to 3 seconds, we travel at a constant speed of 3, even though our speed is actually changing. So I multiply that constant speed by the time, and finally, the final distance we travel from 3 to 4 seconds, I take my constant speed of 5 and I multiply by that last interval of time. I don't have to use this value because I assumed that I was moving at 5 meters per second all the way up till the end. Finally, we add these individual distances from each segment, add those all together, and the total distance we've traveled is 14 meters, which is what we already found. But remember, this 14 meters is not very close. The true value is 17.2. Why is this such a bad value? Because we're making our assumption that the speed is constant over such a big increment of time. So let's use a smaller increment of time. Now we're increasing the time by 0.1 seconds. Here are the velocities, the speeds, at every 0.1 seconds. So I calculate the distance. From 0 to 0.1 seconds, we move at this constant speed of 2, even though the speed is actually changing. So we assume the speed is constant, we multiply that constant speed by the increment of time, which is 0.1 seconds, that's our delta t. We get a distance. In this next interval, I assume we move at this constant speed, even though the speed is actually changing. And I multiply that constant speed times the increment, the delta t, of 0.1, and I get my distance. And I get the distance for every single increment. And again, this last increment, right here, I assume we move at 7.07 meters per second, all the way up till the end. And so I don't need to use this final value. I add all of those individual distances from every interval, from every increment. I add them all up, and my total is 16.94. That's really, really close to the true value of 17.2. So how can I get even better? Instead of using 0.1 seconds, use a smaller delta t. Let's change the time by 0.01 seconds. I'm going to take this velocity and assume it's constant over the first 0.01 seconds. I multiply that velocity by that increment of time, that delta t, and that gives me my distance. Then I assume we have this constant velocity, 2.08, over the next 0.01 seconds to get the second distance during the second interval. And I calculate the distance for every single interval. Wow, that's a lot. All the way up until the end. And again, in this final interval, we assume that we're moving at 7.01 meters per second for the final 0.01 seconds all the way up till the end. So I don't need this last value. And I add every one of those distances together, and what do I get? 17.17. That's really close to the 17.2 meters that we actually travel. Okay, final example. We can get even better by using an even smaller interval, delta t. I'm going to calculate the distance during this first 0.001 seconds. I assume we move at the constant 2. The time interval that we're traveling is 0.001 seconds, and I calculate my distance. In the second interval, I assume we move at this speed for 0.001 seconds, the same interval of time, 0.001 seconds, and I calculate the distance for that second increment from 0.001 seconds to 0.002 seconds. And I calculate this for every single value, every single increment, and there's a lot of increments. That's why this chart goes so far down. And we're almost there. We calculate all of these distances for every single one, and we add them all up, all of those little tiny distances that we travel, and what do we get? Almost exactly 17.2. So what exactly are we doing, and why does it work? We're using the formula for constant speed, even though the speed is not constant. And we're assuming that the speed is constant over really, really small increments of time. And then we calculate the distance for every single tiny little increment or interval, delta t, and we add all of those up. Now, these delta t's are all the same. It was all 0.1 seconds, or all 0.01 seconds, or they were all the same 0.001 seconds. So we can take away the subscript. When we add these up, the way we show that in our formula is we put up here a sigma. And we said we got really good values if we made delta t really small. Graphically, here's what we're doing. We assume we have a constant velocity. Velocity is the height of the graph. And we took that constant velocity and we multiplied by the delta t. How far along the time axis did we travel? But wait a second, we're multiplying height times base, that's area. And then we took the second height, the second constant velocity, we multiplied it by the second delta t, we got another area. And we did this for every increment of time. We calculated the area. And what is this exactly? Well, it's the area under the curve, or under the graph. That's why we say that integrals are the area under the graph. Because if we make these delta t's really, really small, then this shape will actually become the exact area under the graph. Now, when we're dealing with really small delta t's, when we make those delta t's get smaller and smaller and smaller until they're basically zero, we don't call it delta t anymore, we call it dt to show it's a really, really, really small interval. And when we're adding really tiny intervals, we don't use sigma, we use the integral sign, which is another way of writing the sum. And it's easy to remember that this represents the sum because it looks like an S. Now, we've been careless this whole time about whether we're discussing velocity or speed. In reality, we should be talking about velocity. I'm adding an arrow because velocity is a vector, and vectors have direction just like arrows do. Physicists will tell us that if we use velocity here, then we need a vector on the left side as well. And the correct one from physics isn't distance, it's position, very similar concept. This is an integral, and that is the integral symbol. So what is it exactly? Remember where we came from. We were multiplying speed and time. That's what integrals do. They perform multiplication when one of the values, speed, is changing. And we take this multiplication and we perform it over sufficiently small increments or intervals. Intervals so small we can pretend that the speed doesn't change, even though it does. And that is exactly why integrals are the area under the curve, because we're multiplying the y-axis, the height, times the x-axis, the base.